Good. So before you start, so Fabio is a research associate at Imperial College London. It's very active in the field of trying to bring in causality into image generation models. So he will talk today a little bit about how we can generate image counterfactuals. Thanks, Fabio.
Hello, everyone. Hopefully you can hear me well. Thanks for coming. Yeah, I'd like to thank my collaborators first. So we've been working on this topic for a couple of years now. I'm going to start with some introduction to causality first. Don't have that much time, but hopefully you'll find it useful. And then I'll talk about some of the practical things we've been doing as well. Okay, so let's get straight into it. Right, so I'll cover the ladder of causation first. Then I'll explain to you the basic mathematical framework for dealing with causal questions, so structural causal models. And then I'll talk a bit about counterfactual inference and what kind of deep causal mechanisms we need for structured variables like images. And then I'll present some results using causal mediation analysis on medical images, specifically brain MRI and chest X-rays. And the applications will be mainly based on this paper. If you're interested, you can look it up now or after. And also this one, which has to do with evaluating image counterfactuals. Okay, so let's start with explaining to you a little bit about what causality actually is. So as you may know, scientific inquiry is often motivated by questions which are causal in nature. So I have 3 examples here of questions we might be interested in answering. So first one, how effective is a treatment in preventing a disease? If I take this pill, will my headache be gone? Or a more retrospective kind of question, would my grades have been a bit better had I studied a bit more? So causality is simply the relationship between cause and effect. Now I have this nice graph here from a study in the New England Journal of Medicine from 2012. And it shows a very positive, very strong correlation between winning the Nobel Prize and chocolate consumption. And it's grouped by different countries. So we can see that on the top right, Switzerland seems to win a lot of Nobel Prizes and they eat loads of chocolate. So if we look at Sweden, it seems like that secretly Sweden has the best chocolate, since they can eat half as much chocolate as Switzerland and win as many Nobel Prizes. Things are looking a little bit rough for Germany, since they eat a lot of chocolate but can't quite seem to convert those into Nobel Prize wins. So what's really going on here? This is a gif of a disgruntled Judea Pearl. There must be another explanation for this relationship. So this segues nicely into something called Reichenbach's, if that's correct, common cause principle, which basically says that we have 3 options. First one is that chocolate consumption causes you to win the Nobel Prize. When you win the Nobel Prize, for some reason, you start eating more chocolate, or both may be caused by some unknown factor U, which induces some spurious correlation between chocolate consumption and Nobel Prize wins. Now, it remains to be seen what U actually is, but in my opinion, a couple of likely candidates could be GDP per capita or wealth per adult, for example. So the rationale is, if you are a little bit more wealthy, maybe you can afford to eat more chocolate and you're also more likely to win the Nobel Prize. But yeah, it remains to be seen. Okay, so a useful way to think about causal questions is following this ladder of causation, which was put together by Judea Pearl in his book of Why. And the first rung of the ladder has to do with association or correlations. And it basically asks questions like, how would seeing X affect or change my belief in Y? And modern machine learning excels at this task, generally speaking. So all of your predictive models that have already been talked about, modeling P of y given X. The second rung of the ladder has to do with interventions. So you may ask questions like, what will Y be if I do X, if I act in some way? So we can use experiments to learn about causal effects in this way. And interventions are pretty crucial for planning, policy making, and figuring out whether treatments are effective for treating diseases and so on. And the final rung of the ladder has to do with counterfactuals. So asking what if type questions. So what if X had not occurred? And this is essentially imagining thought experiments, deducing causes from observed events. And it's generally very challenging to answer this type of question. Okay, so the basic way we need to approach this is starting with some kind of mathematical framework. So we can organize our thoughts a little bit about what we want to do with these causal variables. So here we have a structural causal model, which is a pretty simple structure. It consists of 3 sets of things, 2 sets of variables, X, which are called endogenous variables. So endogenous means that these variables are caused by factors inside our model. We have another set of variables U called exogenous variables, and these are caused by factors which are external to the model, or they're basically background or initial conditions. And then we have a set of functions, also known as causal mechanisms or structural assignments, that essentially determine the value of each endogenous variable as a function of its direct causes, parents, and some exogenous noise factor. So this equation at the bottom here. So to give you a more concrete example of this, we have a simple 2-variable causal model here. We have 2 endogenous variables, x1 and x2, and 2 exogenous variables, u1 and u2. And we have some the equivalent mechanisms down here in terms of equations. And the thing to note here is that x1 is present in the mechanism for x2, since x1 causes x2. And so acyclic structural causal models can be represented by directed acyclic graphs. So that just means that there are no cycles between the variables in the graph. So on the left-hand side, we have a cyclic example and acyclic on the right-hand side. And the edges in all cases point from causes to effects. And here's some very common structures you may find. So the first one, the confounder, is essentially the chocolate consumption scenario I've already talked about. So x3 can induce spurious correlations between x1 and x2. We have x3 as a collider in the middle and as a mediator on the right-hand side. So x3 essentially mediates the causal effect from x1 to x2. Okay, so then we have this, the observational distribution over this Markovian SCM is unique. And it's Markovian SCM because all the exogenous noises are jointly independent. So they factorize across all the nodes. And each variable in the graph is independent of its non-descendants given its direct causes. So this is known as the causal Markov condition. Another object of interest is the interventional distribution. So SCMs can predict the causal effects of actions by performing interventions. So an intervention on this little example here we talked about previously. An example of a question would be, what would x2 be if we set x1 to some constant c? And when we do this, we replace the structural assignment for the variable we intervene on. So we've set it to this constant c in this example. It is no longer influenced by the exogenous factor u1. And performing interventions induces a submodel MC, and the entailed distribution of this submodel is called the interventional distribution. And this is generally different from the observational distribution we talked about previously. Okay, so counterfactuals consider, so SEMs can consider counterfactual scenarios, so hypotheticals. A couple of examples here. All else being equal, would I have been late had I not missed the train? Or going back to the little SEM example we had before, given that we observed some values for x1 and x2, what would x2 have been had x1 been set to some constant c? Okay, so how do we perform counterfactual inference? There's a couple of ways, but there's one way that involves 3 steps. The first step is called abduction. So we want to update our distribution over the exogenous noise given some observed evidence. So we're essentially inferring the posterior P of U given X, which essentially encodes the current state of the world that is compatible with the observed variables X. The second step is called action. So this is where we perform an intervention or choice. So we may set the value of one or more of the variables in the graph to some constant, some new mechanism that we decide. And we obtain this submodel M subscript C. And the final step is to use this model to compute counterfactuals. So you can think of this in combination with the posterior distribution from the abduction step as simply a forward pass through this graph. So that was a bit abstract. Let me give you a very, very concrete example of how you can compute the counterfactual in this very small graph we have here. So I've defined the mechanism for x1 as this very simple function. So it's 1 plus u1. And the mechanism for x2 is 3 times x1 plus u2. Now the form of the noise terms doesn't matter for now, but let's assume it's uniformly distributed. And we have this counterfactual question here now. So how can we answer this following this graph? So the question goes, given that we observed x1 is equal to 2 and x2 is equal to 4, what would x2 have been had x1 been 5? So let's follow our counterfactual inference steps. The first step was abduction. So we know that x1 was equal to 2. And we know that the mechanism for x1 is 1 plus u1. So that implies that u1 must be equal to 1. And using the same logic for x2, we know that x2 is equal to 4. So we plug in the value for x1 into the mechanism of x2. And we can deduce that u2 must have been -2. Another way to look at this is through the lens of inverting the mechanism of the variables. So if we invert the mechanism with respect to the exogenous noise, then we perform abduction. And these are the closed form solutions for these 2 mechanisms. Okay, so in the second step, we perform an action. So in the question, we wanted x1 to be set to 5. So we simply replace x1 with a value 5. And the prediction step is essentially plugging things in. So we know that x1 tilde is equal to 5. We plug that in. We know that u2 is -2. And we multiply everything together. And we get the solution. So the answer to the question is 13 in this case. So yeah, if you understood this, that was probably the most important slide of the talk. So I'd be happy if you went away with just this knowledge. Okay. Okay, so moving on to deep structural causal models, which is work done a couple of years ago at Imperial by some of my colleagues. So in that work, they leveraged deep generative models to learn these SCM mechanisms. And they developed some techniques to tractably estimate causal effects of interventions and perform counterfactual inference to answer these what-if type of questions we're interested in. Now, the challenge is that abduction is pretty difficult for complex problems like medical imaging. And one of the research questions we've been looking at is whether we can generate plausible high-fidelity image counterfactuals of real data. And if so, how can we evaluate our generated data? Okay, so let's go through some of the deep mechanisms, deep causal mechanisms in deep structural causal models. So the first one to review is normalizing flows. So if you haven't heard of normalizing flows, there's a couple of pretty nice surveys I list on the bottom here. And essentially, they build complex probability distributions by successive invertible transformations of simpler base distributions. So to give you a concrete example of what's happening, this is the 2 moons data set being transformed by these learned functions such that we estimate the density of the data. And this can be trained quite nicely using maximum likelihood estimation. Now for scalar quantities, this is pretty nice because it gives us invertible mechanisms and allows us to perform deterministic abduction. So here, the mechanism for some variable x be a function of its parents, and the noise, like we said. And because we define these invertible transformations, we can invert the normalizing flow and retrieve the noise. Okay, so what's the issue with normalizing flows? It's essentially the fact that they don't really scale that well to images, which is kind of a shame. But there's things we can do using variational autoencoders instead, for example. So in this case, the latent variables in variational autoencoder, this bottleneck layer, essentially can act as part of the exogenous noise for X. The caveat being that abduction then becomes non-deterministic and approximate. So let's look at what the causal mechanism for X actually looks like in a model like this. So we have this function for an image X, which takes in a value of the parents and some exogenous noise. And in terms of this initial VAE, it boils down to 2 components. So we have H, which is an invertible component of this mechanism. And it's essentially the sampling of some observational distribution of the decoder. And then we have a non-invertible component, which is essentially the decoder itself. So that's some deep neural network. And doing this induces a factored exogenous noise composition for X. So we have 2 components, Z and epsilon. And to perform abduction, so to compute this posterior over the exogenous noise, we have this factored decomposition over the encoder and this deterministic sampling, inverting this deterministic sampling transformation. Okay, so again, let me give you some very detailed, concrete example of computing a counterfactual with this kind of model. So the first step, again, is abduction. And this boils down to sampling some latent variables through essentially for propagating the image and its parents through the encoder. The second step, we perform a decoding step and produce some mean invariances. So these applied to images would be pixel-wise mean invariances. And then we want to invert the sampling mechanism. So we use our observed X and we invert the sampling mechanism to obtain the exogenous noise term epsilon here. And then we would perform some kind of intervention upstream and obtain these counterfactual parents, which I denote here as PA subscript X, PA tilde subscript X. And then the final step is to use these exogenous noise terms that we've just inferred, along with the parent conditioning, and feeding them through the mechanism for X to compute our counterfactual. So this is essentially what you would do if you wanted to try and retain the identity of the image whilst changing only some parent aspect or conditioning. Okay, so what's the issue with regular VAs for producing high fidelity image counterfactuals? The issue is that they don't scale that well in terms of image generation quality. So we need something else. We need a a powerful generative model that is still amenable to principal deduction, but can allow us to produce high fidelity counterfactuals. And hierarchical VAEs are a good option for this, since they extend VAEs to multiple layers of latent variables. And yes, so they define a generative model of data, which is like this. We have a likelihood term, we have a prior term, and we have some transition kernels between different layers. And the goal is the same as a standard VAE. So we're optimizing our model to be close to a given data distribution by maximizing the elbow, which is a lower bound on the log marginal likelihood of the data. And some more recent work on deep hierarchical VAEs showed some promising results. The main difference here is that they use what's called a top-down inference model. So the inference is done in the same direction as the generative model. Don't have time to go too much into detail about these things, but if you're interested, definitely check these two papers out. And also the original ladder variation autoencoders, and this one as well. Pretty nice. Okay, so I'm going to take a little quick detour to discuss the connection to the diffusion model, since many of you will have been exposed to diffusion a lot recently. So you can think of these Markovian, or well, you can think of diffusion probabilistic models as a type of these Markovian hierarchical VAEs we've talked about, which use a top-down inference model as well. But the main differences are these three. So the encoder in the diffusion model is fixed rather than being learned. Each latent variable has the same dimensionality as X, and we use a single model with shared parameters for all layers in the hierarchy. But in both cases, they maximize the same lower bound on the log marginal likelihood. And this loss on the right-hand side here, called the diffusion loss, simplifies to the usual mean squared error term of noise prediction that we've seen recently. So yeah, maybe this helps you understand where we're coming from using these hierarchical VAEs. Okay, so let's talk about some of the practical conditional hierarchical VAEs we've been using as deep causal mechanisms. So in the figure there, we have the inference model, or the encoder, on the left-hand side. And then we have the generative model, which is the decoder on the right-hand side. And in this case, we show an exogenous prior. So this just means that latent variables in this three-layer example are independent of the parents, or independent of anything that is observed. Alternatively, we can have a conditional prior. So in this case, the latent variables do get access to parent conditioning. So you end up with a conditional prior over these latent variables. There's also another option where you don't use posterior correction. Posterior correction just means that the prior on a specific layer doesn't see the posterior of the layer above. Just this diagonal line you can see across from H3 to Z2, for example. So that's optional there. And in terms of how you actually put these networks together, you can use standard residual building blocks. You can have a UNet if you like. We explored these two options. One is a bit more lightweight, option 1, and option 2 is an inverted version, which scales a bit more poorly, but performs pretty well. Okay, so the interesting thing about this conditional prior is that it induces a latent mediator. Since the latent variables are no longer exogenous. And this is because they're caused by the parents, which are part of the model. So it violates the exogenous condition for these latent variables. But nonetheless, there's still an interpretation of this type of model as Markovian, since the mechanism for each of the latent variables has its own independent noise. So on the right-hand side here, we have what's called a twin network diagram of both the exogenous prior setup and the latent mediator setup. So on the left-hand side, we have observed parents and observed images X. On the right-hand side, we have the counterfactual parents and counterfactual images that we do not observe. And the crucial thing to note is that they both share the same exogenous noise components. Okay, so what is causal mediation analysis? So causal mediation is the study of how a treatment effect is mediated by something else. So this can help us explain why or how an individual or a variable is responding to certain stimulus or certain inputs. This can be very useful for explainability purposes. And using this latent mediator model, we can estimate the direct, indirect, and total causal effects. So this gives us a sense of what the parents are doing to X and what the mediator or the latent variables are doing to X in a disentangled fashion. And this can be pretty useful to see the effects of our interventions. I wouldn't worry too much about the form of the equations here, but if you're interested, you can refer to the paper for more details. Okay, so here's some quick results. If you want to take a look at our demo, you'll see this in action, which will probably help you understand a lot more than I can in 5 minutes. But essentially here we start with a known data generating process, and we generate these counterfactuals, which preserve identity and obey the counterfactual conditioning. This is a similar example using digits with color. And this is the more interesting example using brains. So we have an observed brain on the top right-hand side and some assumed causal graph, which is the result of an intervention. So we have the counterfactual, whether we intervene on the MRI sequencing, the age, or we perform no interventions at all. We can also look at the direct effect maps, so what's changed as a result of our intervention, and per pixel uncertainties as well. And here's an example of the same thing, but for chest X-rays. The graph is a little bit simpler in this case, since we didn't have access to as many labeled metadata information. But yeah, definitely check out the demo if you want to see this in action. Okay, so how do we actually evaluate counterfactuals? So there's these two theorems that we used in our paper to come up with some metrics for evaluating counterfactuals. The first one says that there's 3 axioms called composition, effectiveness, and reversibility, which are necessary in all causal models. And the completeness theorem states that these properties are sufficient. So we figure out a way to use these counterfactual soundness metrics to measure how well we're doing with our counterfactual inference model. So to give you a quick overview of what these metrics are about, the first one is composition. So the definition is listed down here. So intervening on a variable to have a value it would have had without intervention should not affect other variables. So you can just think of this as how well can you iteratively reconstruct your input. And if you have low composition, then the identity is progressively lost very quickly. If you have high composition and a debiased model, then you should be able to preserve the identity quite well. Second one is effectiveness. So in this case, intervening on a variable to have a specific value will cause a variable to take on that value. So this means that if we intervene to change something, we should observe that change. And a model with low effectiveness will be biased. It may not preserve certain properties that we didn't intervene on. A debiased model will do so. The caveat with this property is it's quite difficult to evaluate in practice, since it can rely on a pseudo oracle if we don't have access to ground truth labels, essentially. So reversibility is the last one. So this one's a little bit tricky, but you can understand it as cycle consistency. So how well can you go back and forth between changing a specific attribute of the image and then going back to the original attribute, and to what extent you lose the identity as you do this multiple times. And this follows directly from composition, actually, from in recursive systems such as DAGs. So when you measure composition using in DAG models, you're basically doing this anyways for free. Okay, so I won't bore you too much with results in terms of numbers and stuff, but one thing we identified is that there's an inherent trade-off between these properties. So we can see here on x-axis, as we abduct fewer and fewer latent variables, we can see that the counterfactual loses effectiveness. So it becomes, in the opposite. As we abduct fewer and fewer latent variables, it becomes more effective. And the opposite is true for composition reversibility. Okay, so that's all I have time for. So we've looked at deep structural causal models and seen that they can generate plausible high-fidelity counterfactuals. We also talked about a couple of things we can do to measure the axiomatic soundness of counterfactuals. And we've shown a model that contractively estimate direct, indirect, and total causal effects for these high-dimensional structured variables. And a couple of limitations include the fact we only considered Markovian SCMs. And although this is a common assumption, it can be quite strong in most cases. And also noting again that measuring counterfactual effectiveness relies on separately trained classifiers, which may come with their own issues and biases. So this is something to look at in the future as well. So in terms of a couple of options for future work, there's a lot of opportunity for using counterfactuals for targeted data augmentation. So this hopefully will show improvements in robustness, sample efficiency, and potentially also fairness issues. There's also opportunities to provide principal causal explanations through causal mediation analysis. This is the stuff we've talked about in this talk as an option. We also would like to continue improving counterfactual soundness, either through better machine learning techniques and better generative models, and in collaboration with medical guidance. And there's also lots of work to do in the theoretical identifiability proofs and providing some plausible assumptions under which we can guarantee sound counterfactuals for images, and also extensions to semi-Markovian and non-Markovian settings, where the associated causal graph may have confounding going on. So lots of challenges there as well, and highly non-trivial for images. So that's it. Thanks.